Hello everyone, welcome to Chem Analysis. So as few of you requested me to solve previous year GATE chemistry questions, so in this video I will solve inorganic chemistry questions of GATE 2019. So let's start this discussion. From the first question we can see that we have to tell about the incorrect statement from this 4 option for interhalogen compound ICl3. ICl3 is a interhalogen compound which can be synthesized by the reaction between iodine and chlorine at lower temperature, and they will generate interhalogen compound ICl3. ICl3 generally exists as a dimer, and the structure of this is like this. It will exist as I2Cl6, that is dimer, and in solid state the structure is like this. There will be a bridging of 2 chlorine ligand with the 2 iodine atom, and the geometry of this dimer compound in solid state around the central atom iodine is square planar, that is the 4 chlorine ligand is oriented in a square plane. Similarly in this case also the 4 chlorine ligand is oriented in square plane. You can symbolize it like this, that is chlorine to iodine coordinate bond, and similarly here chlorine to iodine coordinate bond. That means we can see that option number A is also correct, it exists as dimer, and option number second is not correct, since here is given that the geometry around iodine is tetrahedral in solid state, but in solid state the geometry around the central atom iodine is square planar. And if you see the next two options, we can see that in gas phase ICl3 decomposes in ICl and Cl2 gas. So option number 3 is also correct, and in liquid phase ICl3 decomposes like this. ICl3 exists as dimer, and in liquid or molten phase it decomposes as ICl2 plus and ICl4 minus. That means since there is a generation of ionic species, it will conduct electricity in liquid phase. That means therefore option number D is also correct option. So we can see that only option number B is incorrect, and it is the correct choice for this question. So let's see next question. Here it is asked that among the following carbon allotropes, the one with discrete molecular structure, and here we can see that the options are diamond, alpha graphite, beta graphite and fullerene. We know that in diamond and graphite there is a continuous or infinite array of carbon chain, so these are not a discrete molecular structure of carbon allotrope. Only fullerene is the discrete molecular structure. So we can say that fullerene is the discrete molecular structure of carbon allotrope. Here we have to tell about the incorrect statement about the silicones. Silicon mainly contains silicon oxygen bond, that is silicon oxygen is the backbone of silicon, and there is silicon carbon chain also. That means they are organosilicon polymers, and they are really thermally stable due to silicon oxygen and silicon carbon bond. And from the option we can see that in the first option it is given that they are thermally unstable because of the silicon carbon bond, but they are really thermally stable. So option number 1 is not correct. And in the second option we can see they are insoluble in water, since here is organic part in the side chain. That means in the outer sphere there will be organic part, and they are insoluble in water, therefore silicon are really insoluble in water. So this option is correct. And they are organosilicon polymers, organosilicon in the sense that is there is silicon and carbon bond, that means they are organosilicon compounds, and polymer since there is a long chain of silicon carbon and silicon oxygen bond in the structure. So this option is also correct. and they have stable silica like skeleton, since in silica there is silicon oxygen bond, and in silicon we can also see that there is silicon oxygen bond, so they are stable due to this silicon oxygen bond also. So silicon also contain stable silicon oxygen bond as like silica. So this option is also correct, and we have to identify the incorrect statement. So option number A is the correct choice for this question. Here it is given that the delta 0 value, that means in octahedral complex separation between T2G and EG level for nickel H2O whole 6 2 plus is 8500 centimeter inverse, and we have to tell about the delta 0 values for these two complex, where the ligand metal center is in fixed oxidation state, that is in +2 oxidation state in both the two complexes, but the ligand attached to the metal center is changing. In one case there is chloride ligand, and in another case there is ammonia ligand. We have to tell about the delta 0 values for these two complex in comparison to nickel H2O whole 6 2 plus. And to solve this question, we have to first know the order of the spectrochemical series, that is existence of these two ligand, that is these three ligand, that is chloride minus, ammonia and H2O ligand. And if we see the spectrochemical series, we can see that the field strength of the ligands will follow this order, that is chloride minus will be weak field ligand, after that it will come water, and in between chloride and H2O there is few more ligands. I am just telling the order for these three required ligands. And after that it will come ammonia, that means ammonia will be strong field ligand in comparison to water, and water will be far more stronger than that of chloride. And as we know that with increasing the field strength of the coordinating ligand, the separation between T2G and EG levels in crystal field increases. Therefore we can say that in presence of ammonia ligand, the delta 0 value, that is the separation between T2G and EG level, will be higher than that of water, and similarly for the complex containing water as a ligand will show higher delta 0 value in comparison to the complex in which chloride minus acts as a ligand. Therefore NiCl6 4 minus will show lower delta 0 value in comparison to NiH2O whole 6 2 plus, and NiNH3 whole 6 2 plus will show higher delta 0 value in comparison to nickel H2O whole 6 2 plus. It purely depends on the field strength of the attached ligand. Therefore we can see that option number B is the correct answer. Is it okay? So next question. Here we have to tell about the number of carbonyl stretching bands in IR spectrum of trigonal bipyramidal cis MCO3 L2 complex. First of all, we have to draw the structure of this complex in which the two L ligands will be cis, and the geometry around the central metal atom is trigonal bipyramidal. That means two L ligands will be cis, they are cis, and remaining 3 position will be occupied by carbonyl ligand. Now I have previously uploaded a dedicated video on this topic, that how to calculate the number of carbonyl stretching bands for a given metal carbonyl complex, and if you have not watched that video, I will give the link in the description box. If you want to watch, you can go through the link. To solve such type of questions, we have to first see the point group of the given complex. Here we can see that this compound only contains sigma plane, and the sigma plane will pass containing this metal, this ligand carbonyl ligand, and will bisect this ligand and bisect these two carbonyl ligand, and the sigma plane will pass like this, that it will cut these three, and this sigma plane will contain also this L ligand and CO ligand. Therefore we can see that there is only sigma plane, and the point group for this complex is CS. And as I told in my previous video that the molecule which contains only sigma plane, that is for the molecule containing CS point group, the number of carbonyl stretching bands will be equal to the number of carbonyl units present within the molecule. So we can see here is 3 carbonyl units, so number of carbonyl stretching bands will be 3. And if you want to know many more examples, you can watch my previous video. This is a question from nuclear chemistry, and here we have to tell about the total number of alpha and beta particles emitted during this radioactive decay. To solve this question, first of all we have to know the effect of alpha elimination and beta elimination on the atomic number and the mass number change. If a nucleus emit alpha particle, that is mainly helium nucleus, there is a decrease in atomic number by 2 unit and decrease in the mass number by 4 unit, that is for alpha particle decay. And if a nucleus emit beta particle, that means that is a electron, the atomic number will increase by plus 1 unit only. So here first of all we have to see the change in the mass number. Here we can see that mass number is decreasing by 28 units, and on the mass number there is a effect of alpha elimination, so we can say that there will be elimination of 7 alpha particle, and for elimination of 7 alpha particle there will be decrease in 28 mass number, and similarly there will be also decrease in atomic number by 14 unit, since for each alpha particle there is a decrease of plus 2 unit. That means there will be 14 unit decrease in the atomic number. And 28 unit decrease in mass number. So after elimination of 7 alpha particle from uranium 92 to 38 nucleus, there will be generation of one radioactive nucleus whose mass number and atomic number will be like this. Suppose there is a generation of X nucleus for which the atomic number will be 14 unit less, that means 78, and mass number will be decreased by 28 unit and it will be 2010, and similarly later it will liberate or decay beta particle and generate this Pb nucleus, and here we can see there is a increase of 4 unit in the atomic number. Therefore we can say that there will be elimination of 4 beta particles, since each beta particle elimination result in plus 1 increase in the atomic number. So it will generate Pb82 210, since after beta elimination there will be no change in the mass number. Therefore we can see that there is 7 alpha particle and 4 beta particle elimination for this radioactive decay, and the total number of eliminated particle is 11. In these questions we have to choose about the pair in which the experimentally observed magnetic moment values is equal to the spin only values. Now for the transition element, we know that if there is no orbital contribution, then the magnetic moment will be equal to the spin only values, and in case of lanthanide elements, since here we can see that in combination with one transition element there is one lanthanide elements, and in case of lanthanide elements the experimentally observed magnetic moment values will be equal to the spin only values only for F0, F7 and F14 electronic configuration. So first check the first option. Here we can see that chromium is in +3 oxidation state, that means it is D3 electronic, it contains D3 electronic configuration, and the electronic distribution in octahedral complex in octahedral geometry will be T2G3, and it does not show any orbital contribution since T2G is half filled. If T2G is unsymmetrically filled, then there will be orbital contribution, and for this case mu experimental value will be equal to mu spin only values. Okay, and for the second case, that is gadolinium 3, it is F7 electronic, it contains F7 electronic configuration, and as I said, for lanthanide elements, the element which contains F0, F7 and F14 electronic configuration, mu experimental is equal to mu spin only. So for the first pair, we can see that the experimental observed magnetic moment will be equal to the spin only values. You can also check the remaining options. For the option number B, here cobalt is in +2 oxidation state, that means D7, and the electronic configuration will be T2G5 Eg2. That means since T2G is unsymmetrically filled, there will be orbital contribution and mu experimental will not be equal to mu spin only. But in the gadolinium case, it is mu spin only is equal to mu experimental, but we have to tell for the pair in which for both the elements mu experimental will be mu spin only. So option number B will be not correct. And similarly for the third case, for chromium 3 mu experimental will be equal to mu spin only, but for dysprosium 3 the mu experimental will not be equal to mu spin only. And similarly for the lutetium 3 plus, it is F14, it contains F14 electronic configuration, that means mu spin only is equal to mu experimental, but terbium 3 plus mu spin only is not equal to mu experimental, since it does not contain F0, F7 or F14 electronic configuration. So this remaining 3 option is also not correct. Is it okay? This is a question from silicate chemistry, and we have to match the type of silicate for the given 3 varieties with the different type of silicate. For the first option, that is zircon ZrSiO4, we can see that the silicon unit is SiO4 2-, and it is for orthosilicate. The structure is for orthosilicate. And for the second option, that is beryl Be3Al2Si6O18, if we only write the silicon part, that is silicate part, it will be Si6O18 12-, and we can also write it like this, SiO3 6 into 2. That means it is similar to like this, SiO3 N minus 2N, and it is a representation for cyclic silicate. So that means beryl is cyclic silicate, that is 1 is orthosilicate, 2 is cyclic silicate. And for the third option, that is pyrophyllite, it is Al2OH2 Si2O5 2. That means for the silicate part, we can write it like this, Si2O5 whole 2 4-, since the oxidation state, since the charge for this silicate part will be 4-, since aluminum is +3 and OH is -1, so the net charge upon Si2O5 unit will be 4-. And we can also write it like this, Si2O5 N minus 2N. That means it is a symbol for seed silicate, that is 3 is for seed silicate. Therefore we can see that 1 is orthosilicate, 2 is cyclic silicate, and 3 is seed silicate, and option number A is the correct answer. Okay. In cyclic silicate, each SiO4 2- unit will share 2 oxygen atom with the neighboring SiO4 2- unit, and in case of seed silicate, each SiO4 2- unit will share 3 oxygen atom with the neighboring SiO4 2- unit and generate the seed silicate. This is a very easy question. We have to tell about the product for the reaction between Mn2CO10 with Br2, and it will be governed by the 18 electron rule. in the Mn2CO whole 10, if we count the number of electron around the manganese center, we can see that manganese is manganese in zero oxidation state. That means it will contain 7 electron, D5S2. That means 7 electron for manganese and 10 electron will come for 5 carbonyl unit, that means 17, and 1 electron for manganese bond. That means is the manganese center is 18 electron in the starting material, and in the product also manganese center will contain 18 electron. And if we react this Mn2CO whole 10 with Br2, the generated species will be MnCO5 Br. That means 2 unit of MnCO whole 5 Br. And in this case, if we count the number of electrons, that means for manganese it will be 7, for 5 carbonyl units 10, and 1 bromine atom it will contribute 1 electron, that means total 18 electrons. And it will be purely, the reaction will be governed by the 18 electron rule. So we can say that option number A will be the correct answer. And for the remaining 3 cases, if you count the number of electrons around the central metal center manganese, you will see that these 3 options does not contain 18 electron for the central manganese center. In this question, we can see that we have to tell about the correct molecular representation for this tungsten Cp2CO whole 2 complex, and these questions can also be solved depending on the 18 electron rule. And here Cp is a ligand which can coordinate in a flexidentate manner. That means in one way it can act as a monodentate or tridentate, or as one time it can also act as a pentadentate ligand. That means it acts in flexible way. And if we count the number of electron around the central tungsten metal center, for tungsten there will be, since it is below chromium, it will provide 6 electron, and for 2 carbonyl ligands there will be 4 electron, that means in total 10 electron, and we need another 8 electron to fulfill the 18 electron around the central metal center. And this 8 electron will be donated by the 2 Cp ligand, that is cyclopentadiene ligand. In the given option, we can see that for the first case the tungsten is not in 18 electron configuration. For the second case, it is also not in 18 electron configuration, since Cp eta 5 Cp will contribute 5 electron and eta 1 Cp will contribute 1 electron. That means 2 Cp ligand is contributing 6 electron, and tungsten will contain 16 electron instead of 18. But for the third case, we can see that for tungsten it is 6 electron, 2 carbonyl ligands 4 electron, that means 10, and 1 eta 3 Cp will contribute 3 electron, and eta 5 Cp will contribute 5 electrons, that means 2 Cp ligand will contribute 8 electrons, and as a whole the tungsten metal center will contain 18 electrons, and this will be the correct molecular representation for this tungsten Cp2CO2 complex. And for the last case, we can also see that here the tungsten is containing 20 electrons, since 2 Cp ligands is contributing 10 electron, and for tungsten and carbonyl ligands there is coming 10 electrons. So as a whole there is 20 electron around the metal center. But according to 18 electron rule, the metal center try to contain 18 valence electron in a complex. So option number C is the correct answer. This is a question from bioinorganic chemistry. We have to match the 2 column. The first option is given as it is ferritin, and it acts as a metal storage protein, so it will match with option number 3. And rubidoxine, it is a electron transfer iron protein, so it will match with 1. And cobalamin is a cobalt containing enzyme, and it acts as a methyl transfer agent. And carbonic anhydrase, it acts as a acid base catalyst, and it is used in acid base catalysis. So if we see the option for P, it is 3, for Q it is 1, for R it is 4, and for S it is 2. So option number B is the correct answer. This is a very important and conceptual based question, so try to understand carefully. Here we have to tell or identify the ligand for which this redox reactions occurs very slowly. Here the charge 3 plus and 2 plus is for when X is anion, that is like chloride or azide, it will be plus 2 and cobalt center will be in plus 3 oxygen state, and when the X is neutral the charge will be 3 plus and the central metal will be in plus 3 oxygen state. And from the given reaction we can see that the X ligand is changing its position from the cobalt complex to chromium complex. As we can see in the product, the X is shifting to the chromium center, and for this reason we can say that this electron transfer is inner sphere electron transfer, since there is a change in the ligand from one coordination sphere to another coordination sphere. In inner sphere electron transfer mechanism we can see that the ligand combine two coordination complex, and in the last there will be transfer of ligand from one coordination complex to another coordination complex, or in some cases there will not be ligand transfer. If there is a transfer of ligand, we can surely say that the electron transfer is inner sphere electron transfer. Okay. Now the inner sphere electron transfer will be favorable when the ligand will be more coordinating. That means if the ligand is anion, then it will prone to coordination with the metal center, that is chromium metal center, and the electron transfer will be faster. But we have to tell about the slowest electron transfer rate, so the anionic ligand will not be the correct choice for this question. And for the remaining two neutral ligands, if the field strength of the ligand increases, then it will make the complex more inert for electron transfer, and therefore the electron transfer will be slower. And between the H2O and NH3, NH3 is a strong field ligand in comparison to H2O, and therefore it will make this cobalt complex more inert, that for the electron transfer, and therefore electron transfer will occur slowly in case of when X is ammonia ligand. Therefore we can say that the electron transfer will be slowest when X is ammonia. Okay. If you feel any difficulty, then let me know in the comment section. I will try to solve your query. So next latter question. This is the last question for this discussion. Here we have to tell about the molecular formula of the final complex, in which when the complex, that is the complex containing chromium ion, 1 chromium ion, 3 bromides and 6 water molecules, and upon addition of excess silver nitrate, 1 gram of aqueous solution of this complex gave 0.94 gram of silver bromide. We have to tell about the molecular formula for this complex, and for this to solve this question we have to first calculate the molecular weight for the given complex and as well as for silver bromide. Since in the complex there is 1 chromium ion, for chromium atomic weight is 52, and there is 3 bromide, that means 3 into 80, and there will be 6 water molecule, and for each water molecule atomic weight is 16 plus 2, that means 6 into 18, and the total atomic weight for the complex will be, that means total atomic weight for the complex is 420, and for silver bromide the atomic weight will be, this is atomic weight for chromium H2O whole 6 Br3. This is the empirical formula for the complex. We have to tell about the correct molecular formula, that means how many number of bromide unit is within the coordination sphere or outside the coordination sphere, and for that we have to identify that how many mole of silver bromide is precipitating by reacting with this complex and silver nitrate. Since the reaction with this, when we react with this complex silver nitrate, then there will be precipitation of silver bromide. Depending on the number of silver bromide precipitating, we can tell about the number of bromide outside the coordination sphere, and the molecular or atomic weight for this silver bromide will be, for silver it is 108 and bromine it is 80, that means 188. Since from the given question we can see 1 gram of aqueous solution of the complex, 1 gram aqueous solution, that means 1/402 mole, and if you calculate this, that means 2.38 into 10 to the power minus 3 mole of this complex react with silver nitrate to precipitate 0.94 divided by 188 mole of silver bromide, that means 0.005 mole of silver bromide is precipitating. That means this number of mole complex is precipitating 0.005 mole silver bromide. 1 mole of this complex is precipitating how many mole of silver bromide we have to calculate, and we will get by dividing this unit by the mole of the complex, this mole of silver bromide. It will come near about 2. Therefore we can say that outside the coordination sphere there will be 2 bromine atom, and the molecular formula for this complex will be this one, that is option number B is the correct answer. Is it okay? Okay, if you feel any difficulty, then let me know in the comment section, or you can send me a mail, as the mail ID is given in this video. So that's all for this discussion, and thank you for watching. If you like this video, you can also share it with your friends, and if you are new in this channel, then please subscribe to my channel Chem Analysis to get such interesting videos in future. Thank you.